Today we're going to be covering the forced response of our circuits due to a sinusoidal input excitation. So the first thing that we're going to do is we're going to revisit the concept of a forced response. And to do that, we're going to first look at this simple DC circuit. So in a DC circuit, we have a DC excitation source, this voltage source, Vs, and we are trying to figure out our response, I. Because this is a DC circuit, we can easily figure out what that is, right? To a DC circuit, the inductor looks like a short circuit, and so our response, I, is simply Vs divided by R. So if we put in a DC excitation source, we get out a DC response. Well, we're going to see that if we instead sinusoidally excite a circuit, so let's say that we put in Vs of t, and we're trying to determine I of t, that if Vs of t is of the form Vm cosine omega t plus some phase angle theta v, a simple sinusoidal excitation voltage, we should observe that our current I of t will be of the form Im cosine omega t plus some phase angle theta I. So if we put in a sinusoidal excitation voltage, we get back a sinusoidal response current where the magnitude of our response will be different than the magnitude of our excitation. The frequency of our response will be the same as the frequency of our excitation, and the phase angle of our response may be different than the phase angle of our excitation. Excuse me. So we're going to work this by applying Kirchhoff's voltage law and figuring out how we can determine this quantity Im and this quantity theta I given our circuit parameters. So I can define the voltage drop over my resistor to be Vr of t, positive polarity on the left because I want my current I of t flowing into the positive polarity terminal. Similarly, here is VL of t, positive polarity on top. If I apply Kirchhoff's voltage law around this loop, I can see quite easily that Vs of t is equal to Vr of t plus VL of t. And so what I have then is Vm cosine omega t. And to make our math easier, we're going to work under the assumption that this guy is 0 degrees for now. It's just going to make the bookkeeping a little bit easier. So Vm cosine omega t will be equal to, according to Ohm's law, if I of t is on this form, then Vr of t should just be R times Im. So that's going to be R Im cosine omega t plus theta I. We don't know that this is going to be 0, so we can't leave that out. Plus L d by dt of Im cosine omega t plus theta I, like so. If we perform the indicated derivative, then what we're going to get is R Im cosine omega t plus theta I plus omega L times Im. Let's see, the derivative of cosine is negative sign, I believe. So we should have a negative sign right there. Yes. Plus theta I, like so. And what I'm going to do is I'm going to use trig identities to express this function cosine omega t plus theta I as the product of sinusoids, and also express sine omega t plus theta I as the product of sinusoids. So using trig identity number 6 on your worksheet, this is going to become r times Im cosine omega t plus theta I is going to be cosine omega t cosine theta I minus sine omega t sine theta I minus omega L Im, and then sine omega t plus theta I is going to become sine omega t cosine theta I plus cosine omega t sine theta I. And it looks like we've made the math a bit more complicated, and we certainly have, but we can group like terms. So what I mean by that is we are going to have, let's see, well, actually, let's do something here. Okay, so let's call Im cosine theta I as a coefficient of A1. And let's call A2 negative Im sine theta I. So if we substitute these relationships in, so we have an Im cosine theta I here, so that's going to be R, we're going to have Vm cosine omega t is equal to R times A1 times cosine omega t. So that takes care of this guy. We're going to have, we have a negative Im sine theta I here, so we're going to have minus RA2 sine omega t. We have an Im cosine theta I here, so we're going to have minus omega L A1 sine omega t. Actually, let me move that down because I think I'm going to run out of room here. And then here I have minus omega L. Well, I have minus and then sine, so that's going to be plus A2 cosine omega t. And so if I group my terms together, so I'm going to have R A1 plus omega L A2 cosine omega t minus R A2 plus omega L A1 sine omega t is equal to Vm. So RA1 cosine omega t plus RA2 sine omega t. Let me check the sign on that real quick. So I have negative sine theta I. Okay, so this should be a positive sign there. Minus omega L A1 sine t plus omega L A2 cosine. Okay, so plus here, minus here. Sorry about that. Alrighty, so you may be thinking to yourself, and I wouldn't blame you, why did we do all of this? Well, we have a magnitude times the cosine function is equal to a magnitude times the cosine function plus some other magnitude times a sine function. And so we can develop a system of equations from this. And by that, I mean Vm must be R A1 plus omega L A2, right? This is a method of undetermined coefficients, I believe is what it's called. So if we know the coefficient of the cosine term on the left-hand side of the equal sign, that has to be equal to the coefficient of the cosine term on the right-hand side of the equal sign. Similarly, we could see that 0, which is the coefficient of the sine term on the left-hand side, must be equal to R A2 minus omega L A1. So we have a system containing two equations with two unknowns, A1 and A2, and we can solve these. We find that A1 is, excuse me, R times Vm divided by R squared plus omega squared L squared, and A2 is omega L Vm divided by that same denominator. Excuse me. Now our goal is to get Im and theta I in terms of R, L, and Vm. We can actually do this by setting this equation for A1 equal to this equation for A1 and this equation for A2 equal to this equation for A2. And so what I mean by that is that if Im cosine theta I, which is A1 squared, plus Im sine theta I squared. So this is A1 squared plus A2 squared is going to be Im squared times cosine squared theta I plus sine squared theta I is simply Im squared, because cosine squared of an angle plus sine squared of an angle by definition is 1. And so from this, we can see that Im is the square root of R Vm divided by R squared plus omega squared L squared, quantity squared, plus omega L Vm divided by r squared plus omega squared L squared quantity squared. Excuse me. So we're going to have so we're going to have r squared Vm squared in the numerator here, omega squared L squared Vm squared. We're going to have a common factor of Vm squared that we can pull outside. So we're going to have Vm squared, the square root of that gives us Vm. R squared plus omega squared L squared from squaring these numerator terms divided by r squared plus omega squared L squared quantity squared. Well, this cancels that, and we are left with the magnitude Im is simply Vm divided by the square root of r squared plus omega squared L squared. So we have developed a mathematical relationship that gives us our magnitude in terms of our parameters. Now, to get our angle, I'm going to have to, erase some of this. So let's erase this bit right here, because we're no longer using it. So the tangent of theta I is defined to be the sine of theta I divided by the cosine of theta I. It would not change our relationship at all if we put a common factor of Im in both the numerator and the denominator. And since we're expecting A2 to have a negative sign, if I put a negative sign here, it's the same as putting a negative sign here. So from this, we can see that theta I is equal to the negative inverse tangent of A2 divided by A1. So A2 is omega L Vm divided by r squared plus omega squared L squared divided by A1 r Vm divided by r squared plus omega squared L squared. We can see that there's a common denominator here that's going to cancel each other out. And then in the numerator, there's a common factor of Vm. So theta I is negative the arctangent of omega L over r. We can put these results together and find that I of t is then equal to Vm divided by the square root of r squared plus omega squared L squared cosine omega t minus the inverse tangent of omega L over r. So this is our result. We now have figured out, based on these circuit parameters of R, L, and the magnitude of the voltage that is applied, that we can determine the current. We can determine the magnitude of the current, and we can determine the phase angle of the current. The problem that we're facing here is that, gosh, we just did a bunch of rather difficult math using multiple trig identities and things like that to get the result for an extraordinarily simple circuit. And if we increase the level of complexity of this circuit simply by placing another resistor in parallel with this inductor, we would have to develop a whole new system of equations and all that kind of good stuff that would just make things very, very difficult to solve. When we come back, we're going to look at the first simplification that we can make in solving this style of circuit. So before we make our first simplification to making analyzing sinusoidally excited circuits easier, I'd like to explain exactly why I'm going to do what I'm doing. And so let's start by looking at a black box network. So I have a generic black box network. And I have observed, here's my input terminals, and here are my output terminals. I have observed that if I excite this system with a function x of t, where x of t is a voltage Vm cosine omega t plus some phase angle theta v, my response y of t will be of the form Im cosine omega t plus theta I, where if I suffer through enough math, I can figure out how to express Im in terms of the circuit elements used to form the linear black box network and the magnitude of the excitation function. Now, let's look at this exact same linear black box network, except we're going to apply a slightly different excitation function. Let's call this guy x1 and this guy y1. So if I apply an excitation function x2 of t, where x2 of t is Vm sine omega t plus theta v, then I should observe a response of the form y2 is equal to Im sine omega t plus theta I. Now it should be pretty obvious that if I put in a cosine function, I expect to get out a sine function. Or excuse me, if I put in a cosine function, I can expect to get out a cosine function. And if I put in a sine function, I can expect to get out a sine function. But if you're unsure of that, we could simply do a transformation on this, right? Cosine is equal to sine plus 90 degrees or minus 90 degrees. I don't remember off the top of my head. Trig identities 1 and or 2 from your sheet. So it shouldn't be any stretch of the imagination then by applying those trig identities to get these results. Where it might take a little bit of a leap of faith is remembering the homogeneity property of linearity. The homogeneity property of linearity, also known as the scaling property of linearity, says that if I scale my input by some non-time varying factor, I can scale my output by that same factor. So if I doubled my voltage, I would get double the current. Well, what I'm going to scale it with is the imaginary operator j. This does not vary with time, so this is actually a perfectly legal move. So if I scale my input by a factor of j, I'll scale my output by that same factor of j. Now, why this is important is our third case. We have our same linear black box network. But now I'm going to excite it with x1 and x2 simultaneously. So x1 and x2, that's going to be, so my total x of t is going to be Vm cosine omega t plus theta v plus j Vm sine omega t plus theta v, which, using Euler's identity, is simply Vm e to the j omega t plus theta v. My response to this, due to the linearity, or excuse me, the additivity property, my response, y of t, should then be Im cosine omega t plus theta I plus j Im sine omega t plus theta I, which I could express using Euler's identity as an exponential function, but I'm not going to. Let me explain why. What this is telling us is that if I apply a complex excitation, the real portion of the output corresponds to the real portion of the input, and the imaginary portion of the output corresponds to the imaginary portion of the input. So what I could do is I could analyze this circuit using a complex excitation or forcing function, determine the output due to that complex forcing function, and then take the real part of it, and I will get the exact same result as if I had just applied the cosine function by itself. And we're going to do just that, and we should see that the math behind this method, while still a little difficult, is significantly easier than having to deal with all of those trig identities and setting up systems of equations and things like that. So, what I'm going to do is I'm going to say that this Vs of t that I've defined right here is simply the real part of Vm e to the j omega t, where again I'm holding my phase angle to be 0 just to make my math easy, and that my response will be the real part of Im e to the j omega t plus theta I. So here's my KVL equation. So this is going to give me, if I put in what I have for my excitation function now, Vm e to the j omega t will be equal to R times my current. So this is R Im e to the j omega t plus theta I plus L d by dt of Im e to the j omega t plus theta I. If I take my indicated derivative, I'm left with R Im e to the j omega t plus theta I plus j omega L Im e to the j omega t plus theta I. Now, e to the j omega t plus theta I is the same as e to the j omega t times e to the j theta I. So the sum of these arguments of this exponent can be broken up into a multiplication of exponents. So I can factor out a common factor of e to the j omega t from everything, which would leave me with Vm is equal to R times Im e to the j theta I plus j omega L times Im e to the j theta I. I'm going to give myself a little bit more room here, so please just try to remember what was going on. Actually, so what I'm going to do now, I can factor out Im e to the j theta I. Im e to the j theta I, which is just a polar or exponential form complex number, will be equal to Vm divided by R plus j omega L. Now this may not seem like much, but I want you to notice we have a complex number in polar form on the left-hand side and a complex number in rectangular form on the right-hand side. And since we know how to swap between those two forms, we can actually determine Im and theta I from just this relationship. So, for example, what I'm going to do is I'm going to multiply this guy by R minus j omega L divided by R minus j omega L. This is simply the complex conjugate of the denominator divided by the complex conjugate of the denominator, which is just a fancy way to express the number 1. But it's going to allow us to get rid of the complex number in our denominator. So this is going to give me Vm times R minus j omega L divided by R squared plus omega squared L squared. And I am going to expand this out to a distinctly rectangular complex number where I'm going to have Vm R divided by R squared plus omega squared L squared minus j times omega L Vm divided by R squared plus omega squared L squared. Now, Im is the magnitude of the complex number on the left-hand side. And so it must be equal to the magnitude of the complex number on the right-hand side. Well, hopefully you all recall that the magnitude of a rectangular complex number is the square root of the real part squared plus the imaginary part squared. So this is going to be Vm R divided by R squared plus omega squared L squared, quantity squared, plus negative omega L Vm divided by R squared plus omega squared L squared, quantity squared. We have a common factor of Vm squared in each denominator that we can pull out. So we're going to have Vm multiplied by the square root of R squared plus omega squared L squared divided by R squared plus omega squared L squared, quantity squared, gives us Vm divided by R squared plus omega squared L squared. So we got the exact same result as our very long and trig identity laden method working purely in the time domain. Theta I will be, by definition, the arctangent of the imaginary portion divided by the real portion. So that is negative omega L Vm divided by R squared plus omega squared L squared divided by R times Vm over R squared plus omega squared L squared. These denominators cancel, the Vm cancels, and negative the angle inside is the same as negative outside of the arctangent operation. So we get negative arctangent omega L Vm. So from this, I of t will be the real part of Vm divided by r squared plus omega squared L squared e to the j omega t minus the inverse arctangent of omega L, excuse me, that should be over r. Which is just, using Euler's identity, Vm divided by r squared plus omega squared L squared cosine omega t minus the arctangent of omega L over r. So we get the exact same results, but in my mind, the math was much, much easier to do. Really, the hardest part here was knowing that if I multiply by the complex conjugate of the denominator over the complex conjugate of the denominator, I'll be able to express this rectangular form fraction as a rectangular form complex number that doesn't have any complex numbers in the denominator, which was a lot of words together. Hopefully they made sense. So this is where we are going to stop for today. But please note, so the next thing that we're going to do is we're going to introduce the concept of a phasor. And a phasor is just a shorthand notation for doing exactly what we have done here that eliminates even more of the math. So it'll make things, simplify things one step further. Thank you for watching.